All right, so in this video, I'm going to show you what I call the second method in which we can solve discrete dynamical systems using Google Sheets. And the difference between the first method we did and this method is we're not going to define any parameter values using named ranges or anything fancy like that. Every parameter we have for a model, we're just going to rewrite as a different column. So for this model in particular, we only have one real parameter, that's that parameter k, but we do have that other initial condition p sub 0. And to give you a sense of how I plan to organize this, we can start writing stuff in Google Sheets right away. We'll have a column that's dedicated for a parameter. In this case, we'll make that parameter k. And if we had more parameters, we would just create more columns just like this. The next column we could make is just our iteration number n. After that, we can start off with our usual p sub n and the p sub n plus 1. So the current iteration and the next iteration, the n plus first. So in this case, our value of k, if we start off with the similar initial conditions as the previous video, we'll set k as 0.25. Now what we can do that's a little fancier, if we just want to change the value of 0.25 and it changes k everywhere in this document, is, well, the way we're structuring this is a very row by row fashion. So if we write underneath in grid cell A7, directly below where we wrote 0.25, we could define that to be equal to grid cell A6. Similarly, in AH, we could write that to be equal to, say, A equals A7. And once we've done that twice, we can see that we could highlight, click and drag using the bottom right corner, and Google Sheets will pick up on a pattern. So now if we change that value of 0.25 to say 0.55, it should change all of those k's in that row accordingly. All right, so let's go back and reset our n value, or counting index. So we started off at n equals 0. That's where our initial value was defined. Remember, at p0, or n equals 0 in that case. So we'll type 0, click enter, 1, click enter, 2, click enter, 3. Once we've done that a couple times, instead of having to keep clicking enter, writing those integers, we can use Google Sheets pattern recognition, highlight those cells, hover over the bottom right corner, click and drag. Excellent. So what's the thing we haven't used anywhere? We haven't started with our initial value. So our initial value in this case was given by 10. So in item C6, directly below where we have p underscore n, we can just write that as 10, hard code that in. At that point, well, to get the next iteration, the p first value just depends on the 0th iteration value of p0. The second iteration just depends on p1, third iteration depends on p2, and so on. We're going to see this cascading diagonalization argument again. So again, I'll just set this up. So if we have n p0, or sorry, not p0, but pn plus 1, we would have 0, 1, 2, 3, 4, etc. in the n column. Under Pn, we would have, well, if n equals 0, we have P0. If n equals 1, we have P1, P2, P3, and so on. And under the n plus first column for P, well, if n equals 0, that means we're looking at the next iteration, which is P1. If n equals 1, we're looking at the next iteration now, that's P2. If n equals 3, we're looking at the next, or n equals 2, we're looking at the next iteration, which is P3. And we could keep on doing this process over and over. And what I really want to draw our attention back to is, well, we know this value of P1 is going to show up next to that value of P0 to its right, but we know that that value is going to be the same as the lower diagonal value, or the value directly below P0. So we can do the same assignment of grid cells. So in grid cell, for me, C7, the one that's directly below where we wrote the initial value of 10, we can write equals And then we can make that equal the value or whatever value gets put into D6. And once we do that, we could do that again. So 2 boxes down from, or grid cells down from our initial value of 10, we could say this equals, and then the upper right diagonal element. And once we've done that twice, we can highlight them and use that awesome built-in feature of the click and drag pattern recognition to do that for all the solution values we care about, which in this case looks like going up to the 14th iteration. So at this stage, we've set up our Google Sheet to solve this discrete dynamical system given by this recipe of the next iteration equaling the previous iteration plus k times that previous iteration value. And we're going to do this solution in a very row by row fashion because all of our parameters would be in these successive columns. So a parameter value in a specific row, we will use for that row's next iteration. So in column D6, we can write equals, and our solution again is equal to the previous iteration, which is that value directly to the left. Next, we can write a plus sign, and we have k times the previous iteration. Well, the k for us is found in column A. So it's whatever is in the same row in column A for the k's. And now we need to multiply that by, well, the previous iteration value, which is that value in C6. And we can click enter. Once we've done that, we see the previous iteration or the next iteration value pop into D6 as well as E7. And again, we could keep typing this equation over and over or using that pattern recognition inside of Google Sheets or Excel, highlight and then click on that lower right-hand corner when you see that plus sign come up. And we can click and drag and it'll find all of the successive iterations for us. So if we were to do the same thing, go ahead and try to plot this, we would do the chart making in the same way, going up to insert, clicking on chart, and then basically making sure that we're using the appropriate data. In this case, it actually looks like it defaulted to the correct data, but just for some practice, I'm going to get rid of all the data that's there. So the first thing, we want to make sure that the chart type we're using is a scatter chart. So if it's online, area, bar chart, whatever, feel free to scroll down and just click scatter under chart type. Next, under x-axis, we want to add the independent variable here, which is our iteration counter or the indexing variable n. So we can click select data range and click all the n's that we're solving for, which in this case is 0 to 14. Click enter, and we should see those pop up. Oh, I guess I should have removed the series before. And let's just go back, remove that x-axis just to give us total practice here. Again, adding the independent variable, we go to x-axis, select a data range, and then click the range we want. The n values of our indexing variable from 0 to 14, and we can click enter. All right, nothing popped up. That is a-okay because we've added no dependent variables. So click on add series, and then we can select a data range, and we're going to do this the same way. We want to select the data that corresponds to our dependent variable, which is our actual, in this case, piece of n values, or the iteration values at the nth stage. So once we've highlighted all of those that correspond to n 0 to 14, we can click enter, and you just see our chart pop up. And again, in this case, what's a little different about changing parameters here is if we just went into the A column, randomly chose a parameter, selected, in this case, A14, made it 0.5, it would just throw off all the parameters after that. So we'd have this break where there's 0.25s and all of a sudden 0.5s. In some models, maybe that'll be useful. But if we just want one common parameter everywhere, we would need to, again, reset all those previous ones as 0.25 by doing the click and drag method. But if we go to the very top where we just said, hey, grid cell A6 directly under that description K was equal to 0.25, if we change just that number, everything else should also automatically change. So either you use method 1 or method 2, as long as you change the parameters in the correct locations, just like we could change the initial value from say from 10 to 0.22, we can change the solution automatically. We just have to be careful if we're using method 1 or method 2 to make sure that we're being consistent. I hope this video was helpful.